Okay, last time we talked about the kinetic energy, and I promised that we would take a look at the potential energy. So there is a specific case when the force can be written as the gradient of a scalar potential function. Then it turns out that the work done doesn't depend upon the path, and we are going to prove that now. So let us say the force can be written as a gradient of a potential. So remind you, this is du by dx partial u by partial dy and partial u by partial dz, right? Minus, of course. And notice that this is a vector quantity. The u here is a scalar potential, and the gradient of u is then obviously a vector, right? So let us try to calculate again the work between 2 points 1 and 2, which is equals to the integral from 1 to 2 f dot ds. Okay, and now we insert our formula for the force. So this is then the integral from 1 to 2 gradient of u dot ds. Okay, let us take a look at this term inside here. So gradient of u dot ds, there should be an arrow up here, dot ds, is nothing but partial u by partial x dx, but partial u by partial y dy plus partial u by partial z dz. And if you remember some calculus, this is nothing but the total derivative of the scalar potential energy. So this is equals to du. So the integral turns out to be the integral du between points 1 and 2, and this is just u of 2 minus u of 1. And notice now that the work done here does not depend upon the path taken. It depends only on the values of the potential of the values of the potential at point 2 and 1, at the end point and at the beginning point. So forces like these are called conservative, because what that means is that the energy is conserved, you see. So you cannot gain any energy from this potential by a cyclic operation or so. It always it is conservative, right? So what else I wanted to say about this is what I wanted to say was that, yes, basically we can find out some more things, which is basically we know that W12 is also T2 minus T1, as we found last time, and now we know that this is equals to U2 minus U1, right? So you get let's see. This should be V12 is U2 minus U1. Yes, of course, because I forgot that we have a minus sign over here. So this is going to be minus all of this, which is equals to U1 minus U2. And here we then have U1 minus U2. So if you bring the U2 to the other side and the T1 to this side, then we have T2 plus U2 is T1 plus U1. And this is basically nothing but the conservation of energy. What it basically says is that the kinetic and potential energy at the point 2 is the same as the kinetic and potential energy at the point 1. So what happened was, so the sum of the total energy, the kinetic energy and the potential energy, is conserved. That's what it means. So this is the energy conservation theorem, right? That's all I had to say about potentials, and thank you for watching.